To first explain bonding and geometry in our complex ion exploration challenge, the transition models apply valence bond theory. So we may remember Carbon Man from chapter 20, Organic Molecules, where we learned a bit about valence bond theory and hybrid orbitals of carbon when it makes certain bonds. So for example, we have Carbon Man here, and as you can see, he has the ability to make 4 bonds. Now, these are going to be considered single covalent bonds that come from sp3 hybrid orbital. So we know these aren't just lines, these are going to be specific hybrid orbitals that are created from mixing atomic orbitals of carbon to create brand new hybrid orbitals that allow us to understand how carbon can make stable bonds, okay? So we see here that our carbon is going to be bonded to hydrogen. We have a carbon here bonded to hydrogen. And what we really are saying is that the sp3 hybrid orbital is overlapping with the orbital for hydrogen. And so that overlap is allowing them to create that end-to-end overlap, and that sharing of that electron is allowing them to create a sigma bond or a single bond here. And that sigma bond creates 109.5 degree bond angles, okay, between each of our electron groups here. And because of that 109.5 degree bond angle, we actually have a tetrahedral shape, okay? So let's go ahead and think about that. If you know that you are kind of like already getting confused by those little details or this mini review, you can always go back to brush up on some of those details from Chem 101. But the goal here is understanding that valence bond theory is going to be mixing atomic orbitals to create new hybrid orbitals. And those hybrid orbitals are the orbitals that are used in creating covalent bonds. Okay, so we want to apply this kind of theory to help us understand complex ions. And beyond just applying it to create the new hybrid orbitals like I just talked about, we also want to add in the other layer, which is the shape. So because these sp3 hybrid orbitals are formed and they're going to be forming sigma bonds, of course they can form pi bonds as well if you're going to be having double and triple bonds when we're thinking of valence bond theory for like our main group elements, like a carbon, right? When we're thinking of that, yes, you can have your single, triple, and double bonds. So your sp3 hybrid orbitals, sp2 hybrid orbitals, and sp hybrid orbitals that we talked about in chapter 20. Yes, folks, that is true. We know that. We know when those overlaps happen, shape is going to be informed. So when we're talking about complex ions, we want to kind of think of the same thing. Complex ions, we know that we're going to have our hybrid orbitals, and our hybrid orbitals are going to help us understand shape. And so just keep that in mind as we're going through. All right, folks? But how do we simplify the valence bond theory for ourselves? We said that we had a carbon, and depending on the amount of things surrounding the carbon, that's going to allow us to know the number of atomic orbitals to mix. And of course, that's going to allow us to understand the number of hybrid orbitals that are formed. So for example, if there's 4 things surrounding the carbon, that means that we're going to need 4 atomic orbitals. And the atomic orbitals are going to be the s and p orbitals. So there's 1 s orbital and there's 3 p orbitals, right? And so those 4 orbitals are going to mix to form 4 sp3 orbitals. So we want to make sure that we're basically applying all these little details to complex ions, like I said before. So we will see that complex ions will have their own hybrid orbitals that help inform shape. So remember, the goal is that we're trying to understand why we have the different geometries we have. And so just by applying valence bond theory is going to help us understand the coordinate covalent bonds from complex ions and the shapes that inform. All right, folks, let's get into some of the details. Okay, first, when we're talking about complex ions, that means we have a metal ion, okay, that is bound to a ligand. And if we explain this using valence bond theory, we can say that we have a filled orbital of the ligand. So a filled orbital of the ligand is going to overlap with an empty orbital of the metal ion. So the question becomes, how does this overlap happen? We saw the overlap here, we got sigma bonds. So how did this overlap happen here? Well, we know, secondly, if we're talking about complex ions, we're talking about a Lewis acid-base reaction. That means that we're going to have our metal ion, okay, that has the ability to act as a Lewis acid, meaning it's going to accept electrons. And where it's going to accept electrons from? The Lewis base. So we have our metal ion is going to accept electrons from our ligand or the Lewis base. And once it accepts those electrons, we have a Lewis acid-base reaction that occurs. And of course, we're going to form a coordinate covalent bond and a Lewis acid-base charged complex ion. We saw that before. So we have our coordinate covalent bond, and we know that this complex ion can have a charge. You can also, if we want to apply this with valence bond theory, of course, with complex ion, then we want to say that we have an overlapping from end to end. So again, we're trying to add in different language. Now we're saying we have an overlapping of end to end of the metal ion acting as the Lewis acid and the ligand acting as a Lewis base. So they're going to overlap end to end. That means they're forming like a sigma bond, if you will. And of course, the coordinate covalent bond that is formed is based on that end-to-end overlap. All right, folks? And of course, this overlapping is going to create this metal ligand Lewis acid base complex, and that is what we see here. So all we're really doing here is taking some of the verbiage and adding different layers to apply it to our complex ion. Okay, so what else? Next, we can basically finally take our valence bond theory concept of mixing atomic orbitals to create new sets of hybrid orbitals and apply it to complex ions. So first, let's think about what valence bond theory says about our atomic orbital mixing. So let's think of CH4. That means we have a carbon with 4 things surrounding it, right? And so that means we're going to have sp3 hybrid orbitals. We have CH4, and we have a carbon with 4 things surrounding it. Okay? And so we know we're going to have sp3 hybridization. We also can say the same thing if we had a carbon, like say our carbon was double bond to oxygen with the carbonyl group, and we had a hydrogen. We can say that we have 3 things surrounding this carbon, and so it's going to be sp2 hybridized. And again, how do we get this? We basically mixed atomic orbitals from the carbon, the central atom here, our carbon. We took atomic orbitals from the valence shells, and we were able to mix them. So we took an s orbital, and we took 3 p orbitals, and we mixed them to form sp3. Of course, there's 4 of them. Here, we took an s orbital and 2 p orbitals and mixed them to form sp2. And there's 3 of them, and they're all going to be in equal energy. So that's what we want to apply to valence bond theory. We want to basically make sure we're saying how many ligands are now surrounding our central metal ion. And because of that, what type of hybridization or hybrid orbitals are going to be created? And because of that, what kind of bond angles will it have? And because of that, right, what kind of shape will we see? So let's go ahead and add those layers next. Now, I do want to make sure that you are realizing this is a flashcard moment. So I would definitely have on my flashcard probably number 1 here and number 2. And then for this third one, I would use the next portion to basically add in a little chart. So on the front, I would put like valence bond theory for complex ions. On the back, I would say it has to have a metal ion ligand. It has to have a Lewis acid-base reaction and all the products from it. And it also has to be able to mix atomic orbitals, which we will see next. So again, on the back, I would have linear, tetrahedral, square planar. And then octahedral is really the big kahuna for us. It's the one that we're going to focus on a lot when it comes to pretty much the rest of the lecture. You're going to see when it comes to crystal field theory, our only focus will be octahedral. Valence bond theory, I'm going to show you all the different hybrid orbitals. But again, you might see a lot of octahedral as well. So just keep that in mind. So when we're trying to apply valence bond theory to our complex ions, the goal is that we have a central metal. So here's our central metal in all these different hybrid orbital shapes here. And the central metal, depending on how many ligands are surrounding it, is going to help us figure out how many orbitals from the atom, which is going to be the orbitals from the central metal ion, how many orbitals from it are going to mix to form new hybrid orbitals, okay? So that's what we're thinking of here. And why is this important? Because the geometry of the complex ion is going to depend on the hybridization of the metal ion. So first, let's always go back and say, what is hybridization? Well, again, we know there's a number of things surrounding the central atom, but for complex ions, that is now going to be the number of ligands. So if we go back to the previous part and think about that, and we say, wait a minute, didn't we count the number of ligands surrounding a central metal ion? And we called it the coordination number? Guess what? We did. So when you know the coordination number of the complex ion, you can also go further now and get its hybridization / type of orbital used to create that coordinate covalent bond overlapping. So this is all going to be based on the number of ligands surrounding that metal ion, which in turn explains the geometry, folks. Yes, it connects. So we do have our 4 hybrid orbital shapes that can commonly form. We have our linear, our tetrahedral, square planar, and octahedral, like I said before. So for the linear shape, we still have 2 ligands surrounding the metal ion. And so when we have 2 ligands surrounding the metal ion, we still are going to have 180 degrees. And so you can look at the metal here in the center and then the ligand here as well. And these are going to be taking an s orbital and a p orbital. So I just want to remember that we always understand there's always 1 s orbital, there's 3 p orbitals, and 5 d orbitals. So because we're dealing with transition metals a lot, yes, you will see d orbitals come into play here. So for tetrahedral, we have 4 ligands surrounding this central metal ion. And so that means we're going to have the metal here. We have a ligand. We're going to have a ligand coming out this way and a ligand coming out this way. This is going to be sp3 hybridized, and the shape here is going to be tetrahedral. So I just also want to make sure I put linear here and up there. I just got to rewrite it for myself. Okay, get another color. And the bond angles are going to be 109.5 degrees. So that's going to allow us to be able to have this tetrahedral shape that we see here. Now for sp3, what is that really saying? That's saying that the bonds that are in between here, the bonds here, the bond here, and the bond here, bonds here and the bonds here so far, are overlapping. So the sp3 hybrid orbitals from this central metal ion zinc here is overlapping with the orbitals of the ligands here. And that overlapping is causing those potential sigma bonds, because remember, we're talking about coordinate covalent bonds. And so because there's only 1 pair of electrons being donated, then that's why we can basically get away with calling it sigma. Okay, let's move on to square planar. Now we know that square planar also is going to have 4 different ligands surrounding the central metal ion. So it is going to be using 4 different atomic orbitals, but because the metal ion is in a different orientation here, and it's going to be flat, for example, and it's only going to be on a flat square plane as we see it here, the angles are actually 90 degrees. And so we do not end up using every single orbital like we had before. We don't use all the p orbitals. We actually use a d orbital, sp2. And some folks might say, wait a minute, why are we not using the other p orbital? Well, it's all about the most effective overlap. Remember, we're trying to create these orbitals here for this central metal ion, and we're saying that they are dsp2 orbitals. And the goal is that these orbitals are overlapping to form the coordinate covalent bond. And so you want the most stable, effective overlap. And unfortunately, in the shape that we have here, in this square planar shape, because of the shape, the best overlap would be with an actual d orbital than it would be by adding the other p orbital in here. And so the orbital here would actually be dsp2. A little bit different than what we're used to seeing, right? Now, because we're talking about tetrahedral and square planar, and we know that there's 4 things surrounding it, remember that when it comes to different type of exam questions, etc., this will be specified for you. Okay, so in the question itself, it'll say, here's a compound that is square planar. What is the hybridization? That means you don't have to figure it out. You just have to know, hey, a hybrid orbital for square planar will be dsp2. Now, let's go ahead and talk about octahedral, which is what our main focus for the course is going to be, things that are octahedral. We have our central metal ion, and then, of course, we're going to have our different ligands surrounding it. And the different ligands are going to be 6 of them, okay? Now, we can say, okay, it's a coordination number of 6. So when you have these 6 different ligands surrounding you, that means you're going to have and need 6 different hybrid orbitals. So what we end up doing is basically using 2 d orbitals, sp3. Okay, so we use all 2 d orbitals, sp3. Not all 2 d orbitals, all p orbitals, and then 2 d orbitals. That's what I'm trying to say. So this means that in order for this to have the best overlap, so in order for these d2 sp3 orbitals to have the best overlap here with any ligand surrounding them, they need to use an s orbital, 3 p orbitals, and 2 d orbitals to accomplish that. And so that's what we see here, folks. So again, you can want to start making sure that you are putting all the details down. We have sp linear, sp3 tetrahedral, dsp2, which is going to be square planar, and d2 sp3. which is going to be octahedral. Now for octahedral, you're going to have 90-degree angles as well that are created. And so this is how our valence bond theory, the overlapping of these different hybrid orbitals, connect to geometry and how they all brought together. One thing I will say is that Macmillan will often write sometimes this d orbital here. So for example, you will see it written like this in Macmillan, sp2d, okay, or sp3d2, for example. But for our exams, you're going to write it as we see here. So you're going to actually just simply write it as dsp2. You're going to put the d orbital first. So dsp2 here and the d2sp3 there. There's nothing wrong with writing the other way, like you'll see in Macmillan. There's nothing wrong with that, but it's really a preference in notation. But I'm just saying, as far as like practice goes, my brain's going to automatically put dsp2, and so the examples you see in the exams will also put the d orbital first. So that's why I just want to make that clear for you. Okay, folks? Also, again, flashcard moment. You can put complex ion hybridization in the front. You can also put valence bond theory to the front, and on the back, you can put all three hybrid orbitals, the geometries, the angles, and make sure that you add in the fact that we have to have that metal ligand bond, the fact that we have to have a Lewis acid base kind of reaction with the overlapping of these hybrid orbitals and the ligands themselves. So a lot of little details. Now, of course, the last thing we need to do is get into some examples. Okay, so first you want to read the question, and then you want to pull out any words that can help you connect the material. So this says, what type of hybridization, according to valence bond theory, does a square planar platinum exhibit in the complex ion PT NH34 2+? So first we're talking about hybridization. That means I have to make sure, am I talking about linear? Am I talking about tetrahedral? Am I talking about square planar? Am I talking about octahedral? That's what we need to know. I'm just going to start writing that down. And of course, this is based on valence bond theory. But we also know from valence bond theory, you have to have metal ligands complex that is formed from that coordinate covalent bond. Now, we're talking about square planar here, just from the question. So if it's square planar, I know I need to be focused on the fact that it'll have this type of hybridization. Now, they give me this complex. So I'm going to go ahead and write my complex here. Okay. And what we need to know is we can always say, well, what is the coordination number of this complex as well? Because that's going to help us with hybridization. So I will look at my central metal ion here, and I will look at the number of ligands that are attached to it. This is a monodentate ligand. So that means you can also go back to your ligand chart that's actually given to you on a practice exam, for example, and just verify that these ligands are not bidentate, so you don't have to make any multiplication here. This is all monodentate, so this only has 4 things surrounding it. They're saying that it's square planar. So I know that these 4 things are going to be the ligand here, 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 and here. And so I would say that the answer here would be DSP2. I need 4 things, it's square planar, 4 things surrounding the central metal ion. So that means I have hybrid orbitals of DSP2. Next, it says, what type of hybridization does the cobalt exhibit in this complex ion? So again, we have our complex ion. We want to verify that each of these, whether or not they monodentate or bidentate, both bromine and our water are going to be monodentate. So that means we have 4 waters and 2 bromines attaching to our cobalt. So the coordination number here is going to be 6. And so that means we're dealing with something that is octahedral. Okay, so that means we need 6 different orbitals or hybrid orbitals to make those 6 different metal ligand bonds, folks. So let's just say I have a metal, you have a ligand here, another ligand here, here, another ligand here, and another ligand here. So we need 6. And that is going to give us our D2sp3 here. And so that's 3, 4, 5, 6 different orbitals for our 6 metal ligand bond. So this is how I would approach this type of question. And I just want to let you know that the valence bond theory model is easy to help us picture and rationalize bonding and shapes, but it's not going to give us any insight into any of the properties that we're talking about. We have to go further and use other models like crystal field theory. And as we go further in the lecture, you'll even see that these models are too crude. Sometimes you have to go even higher as you go and learn more about chemistry in the future and inorganic units. All right, folks, see you in the next video.